If you've ever spent a long night pushing the same VLAN change across 40 switches by hand, this lesson is for you. Welcome to Stage 8, Lesson 57, SDN and Network Automation. Over the next few minutes, we'll walk through the technologies that turn networks into code: OpenFlow, VMware NSX, Cisco ACI, and the automation tooling around Ansible and Terraform that ties it all together. Here's the roadmap for the next few minutes. We'll start with the core idea of SDN, pulling the control plane out of individual boxes and centralizing it. Then we'll look at how that plays out in the data center with NSX, ACI, and EVPN VXLAN fabrics. From there, we move up a layer to intent-based networking and the controller pattern, and we'll finish with the practical automation stack you'll actually touch day to day. Ansible, Terraform, and Netbox as your source of truth. So before we talk about what SDN is, let's talk about why it exists, the pain it's solving. Traditional networks are box by box. You SSH into each device, type CLI commands by hand, and every box runs its own brain. A single VLAN change might touch 50 switches, take a week, and leave you with no rollback if it breaks. SDN flips that. One declarative config, one controller, pushed everywhere in seconds with Git history behind it. That's the shift from artisanal CLI work to networks as code. To make that shift concrete, every SDN system breaks down into the same three layers. At the top, the application layer, that's where your Ansible playbooks, Terraform, Netbox, or a custom Python script live, expressing what you want the network to do. They talk down through a northbound API, usually REST or gRPC, to the control layer, the controller itself, the central brain. Think NSX Manager, Cisco's APIC, or open source options like OpenDaylight and ONAS. The controller then speaks southbound, OpenFlow, netconf, gRPC, to the infrastructure layer, the actual switches and routers, physical or virtual, whose only job now is to forward packets according to the rules they're handed. Same pattern, by the way, as SD-WAN, public cloud, and Kubernetes. Once you see it here, you'll spot it everywhere. And the protocol that started it all was OpenFlow, born at Stanford in 2008, the first real proof that you could rip the control plane out of the switch and run it centrally. The mechanic is beautifully simple. Every switch holds a flow table, just a list of match action rules. Packet comes in, switch looks for the fastest match, destination IP, TCP port, MAC, VLAN, whatever, and executes the action. Forward here, drop, broadcast, log. No match? Escalate to the controller, which decides what to do and installs a new rule for next time. The switch itself is deliberately dumb. All the intelligence lives upstairs. Now, OpenFlow was the spark. But the protocol that actually runs in nearly every modern data center today is VXLAN. The idea is to split your network into two layers: an underlay, which is just a boring, fast routed IP fabric, spine and leaf, BGP or OSPF between switches, nothing fancy, and an overlay where tenant traffic rides inside VXLAN tunnels. VXLAN wraps the original Ethernet frame in UDP on port 4789, stamps it with a 24-bit VNI, giving you 16 million tenant networks, and the customer still sees a flat layer 2, while the physical network is pure layer 3. The payoff is huge. Spanning tree dies in the core. A top-of-rack switch failure stops rippling across tenants, and L2 problems stay where they belong, in the overlay. Once you've got a VXLAN fabric, you need a brain to program it, and that's where SDN controllers come in. In the data center, two philosophies dominate. VMware NSX lives in software, running inside the ESXi hypervisor itself, so the intelligence sits next to the virtual machine and works on whatever hardware you happen to own. Cisco ACI takes the opposite bet. Push the smarts down into the Nexus 9000 ASICs, driven by the APIC controller, and you get wire speed performance with deep policy enforcement in silicon. NSX wins on portability and multi-cloud reach. ACI wins on raw performance and tight Cisco integration. And of course, Arista, Juniper, NVIDIA Cumulus, and open source OVS all play in this space too. And once you have that controller brain, the next leap is changing how you talk to it. Instead of imperative configs, VLAN 100, interface GI01, switch port access, no shutdown, you describe the end state you want. A policy called web tier prod, members tagged web and prod, allowed from the internet on 443, talking to the app tier on 8080. The controller figures out the rest. That's intent-based networking, and it rests on 4 pillars: translation of business intent into config, atomic activation across every device, continuous assurance that reality still matches intent, and AI-driven optimization to keep it that way over time. To actually deliver on that intent, you need a tool chain, and no single tool does it all. Terraform handles day zero provisioning of cloud and on-prem resources through declarative HCL. Ansible takes over for day 2 config pushes, VLANs, ACLs, BGP tweaks over SSH or netconf. Netbox sits underneath as your source of truth for inventory and IPAM, while Git plus CI/CD wraps everything in version control, code review, and rollback. And when you need raw programmatic access, Python with NetMiko or Napalm gives you per-device control, with Nornir scaling that out concurrently across thousands of devices. Let's make this concrete. Here's a real Ansible playbook that creates a VLAN 200, a guest Wi-Fi network, across 50 switches at once. The first task ensures the VLAN exists using the Cisco OSVLANs module with state set to merged, meaning it's idempotent. Run it 10 times and nothing breaks. It only adds what's missing. The second task loops over a list of guest ports pulled from group vars and assigns them to the VLAN. 20 lines of YAML, 1 command, 30 seconds of execution, versus an afternoon of CLI sessions and a near certain typo on switch number 37. But before you rush off to automate everything, a word of caution. Automation amplifies whatever you already have. If your configs are inconsistent, you'll just deploy broken configs faster, so standardize naming and templates first. Without a source of truth like Netbox, you're automating from spreadsheets and tribal knowledge. Always test in a virtual lab, container lab, or Eveng before touching production. Treat network code like application code with pull requests and reviews. And don't lock yourself to one vendor. Use abstractions like Napalm, so adding Juniper later doesn't mean a full rewrite. So let's pull the whole lesson together. SDN's core move is splitting the brain from the muscle. A central controller decides, while switches just forward, talking through northbound APIs to your tools and southbound APIs to the hardware. In the data center, that looks like NESX or ACI writing on VXLAN overlays. Intent-based networking takes it further. You declare the outcome, the controller figures out the how and keeps it that way. And the tool chain that makes it real is Ansible, Terraform, Netbox, and Git, config, provisioning, truth, and history. Here's your cheat sheet for this lesson. The terms worth burning into memory. Remember the split. Control plane decides, data plane forwards. Northbound talks up to your apps. Southbound talks down to the boxes. OpenFlow kicked it all off on TCP 6653. VXLAN gives you layer 2 over layer 3 on UDP 4789. The VNI is your 24-bit tenant ID, and EVPN is the BGP brain that makes VXLAN scale. Screenshot this one. And that wraps Lesson 57. Next time, we tackle something the industry has been promising for literally decades, actually deploying IPv6. We'll cover dual stack, NAT64, and the transition mechanisms that make migration survivable in a real production network. If this lesson clicked, hit subscribe over at youtube.com, Dargslan, and I'll see you in Lesson 58.